Okay, first item of business. I took a vote in the earlier class and it passed very highly, but we've missed 2 class days for the hurricane, and we have a test slotted a week from Wednesday. I was thinking of delaying it a week so I can have a little more study time. So I just wanted to take a quick vote. Does anyone object to that? You want to have the test next Wednesday? Can be done. Does anybody vote to delay it for another week? Raise your hand. Okay, the motion passes by majority rules for both sections.
Is the homework still going to be due?
I'll adjust it.
Okay.
I'll put a week in there. So I didn't want to do it until I had the class's input. So if you want to take your test next week, Wednesday, I can arrange that. So I'll send an email out to everyone. But I assume people would want the more study time. Okay. So does anybody have any questions about anything before we start? Nope. Okay. So we're in chapter 4, and we're studying stoichiometry and some of the chemical accounting of things. And we start out with the concept of limiting reagents. And we start off with the most general, where we have a huge excess of one thing, and we don't have, and we're limited. It's obvious what we're limited by. So, like when you drive your car. When you're driving your car runs off of fuel and oxygen. You don't worry about the atmosphere running out of oxygen. You worry about your car running out of fuel. So it's a limiting reagent problem, but it's limited. It's the other reactant. It's such an excess, you don't have to worry about it. So now we're going to have a problem here where we don't know what the limiting reagent is just by looking at it. So this reaction here, 2 nitrogen monoxides plus 5 hydrogens makes 2 ammonias and 2 waters. And we have 86.3 grams nitrogen monoxide and 25.6 grams of hydrogen. What is the theoretical yield? What is the most that we can get out of ammonia? So just looking at this, we don't know. We don't know which one is in excess, which one's limiting. So we have to calculate both. So let me show you. So we have 86.3 grams of nitrogen monoxide. And so moles nitrogen monoxide. Oxygen is 14, oxygen is 16, nitrogen is 14. That's 30 grams NO per mole. And then next is a ratio. There is a 2:2 or a 1:1, however you want to put it. Mole ammonia to mole NO. And then 17 grams ammonia to mole ammonia. And same thing for hydrogen. So 25.6 grams of hydrogen. Mole hydrogen, 2 grams hydrogen. And there are 2 moles ammonia to 5 moles hydrogen, and there's 17 grams ammonia to mole ammonia. So, and these middle steps, it's 2:2, and then it's 2:5 right here from the balanced chemical equation. I just did 1:1 instead of 2:2 because the 2's would cancel anyways. So, and this is just 2 times 1 for hydrogen. This is 14 plus 16 for nitrogen and oxygen. Is everybody following where I get all the numbers from? Questions? Okay. So let's look at this. 86.3 divided by 30 times 17. This is 48.9. And then 25.6 divided by 5 times 17. 27.04. And which one do we choose? We choose the lower one. We pick this one. So our theoretical yield is 48.99. Why do we pick the lowest one? Because that's what you're limited by. Like remember we talked about the Happy Meals? So if you have 10 toys and 1,000 burgers, how many Happy Meals can you make? You can make 10 because you're limited by the lowest amount. So the lowest amount is what becomes the theoretical yield. So questions with this one, how this works? Did you want to see the calculator? Raise your hand. Okay. There you go. All right. Next problem. This is for you. 100 grams of oxygen and 100 grams of hydrogen react. How much water will form? So this is the theoretical yield. And there's the balanced chemical equation. Oxygen 16 grams per mole, hydrogen is 1 gram. Is anyone getting stuck? Has no idea what to do? So out here, what's the moles between hydrogen and water? 2 to 2 or 1 mole. So 2 to 2. I kind of just put everything up on the board. Anyone else stuck? Need some help? So if you do the math, the top one should be 112.5 and the bottom one should be 900. So which one is it? So 112.5. But the 900 one has to be wrong because you have 200 grams to start off with and 900 grams of product doesn't work. Right, so that one is wrong. You could probably discount A as well because you have two reactants, both the same mass, and one is limiting, so you're going to have greater than 100 grams of mass, and it'd be very unlikely that it would be a mass, one part mass ratio, so C is probably out too, so you could probably logic your way to B anyways, just by likeliness. So how are we doing? Anybody have any questions with this? Okay, so next thing we're talking about is percent yield. So a percent yield is the actual yield over the theoretical yield. So before I get there, let me talk about this problem here. So we obtain titanium metal from its oxide by this equation, and then 28.6 kilograms of carbon reacts with 88.2 kilograms of titanium dioxide to make 42.8 kilograms of titanium. So limiting reagent, theoretical yield, and percent yield. So this is how we get all our metals. So metals come from ore, O-R-E, ore. And ores are typically oxides. It can be sulfides, various things. They're rocks we dig up from the ground that are reacting with other elements. And we get almost all of our metals this way, with the exception of aluminum. Aluminum, we use a process that uses a lot of electricity. Gold, so gold we either dig straight from the ground as gold, or what they do in Latin America is they put mercury into mud to leach the gold out. That's why the Amazon River's got a lot of mercury in it. It's because of gold, whatever, mining of sorts. And what we do in the United States is we get rocks and we crush them up and get really heavy mud, and we put cyanide into it, and then we leach out gold using cyanide. So we might also do it with platinum. Depends on if we're mining for platinum. Platinum you can find in its pure form in the ground too. So, but everything else we do it this way, reacting with carbon. So, and typically use an apparatus called a blast furnace. And here I'll draw a picture of a blast furnace. So, what you put in the blast furnace, you put ore, you put carbon, also typically known as coke. C-O-K-E, coke, just like Coca-Cola, and also typically calcium carbonate or calcium oxide. So calcium carbonate or calcium oxide either is used. More often calcium oxide, actually. And in the bottom, you blast through oxygen. That's the blast furnace. You blast oxygen through this mixture, and what happens, of course, you heat the heck out of it too. So what happens is you get the molten metal forming the bottom of the vessel, and then you get a layer on top, and this layer, this is called slag, S-L-A-G, slag. And what slag is just typically calcium and magnesium silicates, so impurities. And slag is easy; you can skim it right off. Now, have you ever seen any of those movies like when they're making swords? Like maybe you've seen the blacksmith will take the ore and he'll heat it up and he'll probably like use an accordion or something like that to fan the fire and get all the stuff in. And then takes out this big wad of molten iron, starts whacking on it, and there's sparks flying everywhere. The sparks, that's the slag. That's the calcium magnesium silicates. You pound it, you can hammer it out by using force that way. Or you can use a blast furnace and mix it up and melt it, and all the slag floats to the top. And then you can skim it off. And we typically use a slag. You can use it as a component in Portland cement, so we usually don't just throw it away. We use it as cement or as a part of cement. Sometimes, depending on the composition, we can put it on our crops. So if it's real heavy in oxides, we'll throw it in our crops because that can sweeten the soil. Sweeten, it means make it more alkaline, more basic, because lots of fertilizers tend to make the soil acidic. But okay, then what happens is we have this molten, usually iron. We make a lot of steel. The molten stuff comes up and usually put it in a little channel. At least we used to do it this way. Now we now we usually just take the molten iron out and we do other things to it. Typically, like add carbon to it. So, but back in the olden days. So let's talk about the Industrial Revolution. United States of America, we still make quite a bit of the world's goods here, somewhere along the 20 to 30%. We manufacture here in our country, but the vast majority of goods in the world are manufactured in China and India. So, but back around the 1850s, the United States was where everything was made. So we were the manufacturing capital of the world. And around the Industrial Revolution, people were leaving the farms and heading to the cities to work. And so there were a lot of farmers that were there working in the factories. And when the farmers saw this, they saw all these molten red-hot steel, and they were forming bars. The molten iron would go down channels, and they would just have bars that were being formed. And they said, oh, that looks like a lot like a piglet, like a mama piglet with a bunch of baby piglets suckling on the mama. So so humans, we only have 2 nipples. The other animals, they have series of nipples going down, and then if you've ever seen dogs like this way, cats are this way. There's a litter of children, and they're being milked by their mothers. There's a whole line of them. And they said, oh, that looks like piglets suckling on a mama pig, so this was termed pig iron. So if you hear pig iron, it means just iron. Of course, nowadays what we usually do, most of the iron that we make, we throw 2% carbon into it to make it structural steel. So carbon steel, structural steel is 2% carbon. And that makes iron much, much stronger. And that's what most of our buildings and bridges and whatnot are made of, structural steel, 2% carbon. Carbon's cheap. We can add 10% carbon to form something called iron carbide. Horseshoes are made of iron carbide. It's really rough, it's really robust material, but it's also brittle. So you don't want to, so that's one downside of iron carbide is it's brittle. Typically so some engine parts are made from iron carbide as well, other than horseshoes. We also can nitride steel to make it really hard as well. That's what tools are made of. So if you ever had a lathe or something like that, the tool is typically made of nitrided iron. And we can also add other elements to iron to form the stainless steels. So to have corrosion resistance is one thing. So, and that's typically all done inside the steel mills right there, and then sold as product. But it's pretty much the same. It does copper. That's how we get it. Zinc, lead, all those materials. Lead. So we used to be able to make lead like the time of the Revolutionary War, like in the 17th century, 16th century. You could find galena. Galena is lead ore. It's kind of a black, shiny rock. And you can take that and you can throw that into a campfire. And the heat and the carbon from the charcoal of the campfire can form lead metal. And then you could take that lead metal and you can melt it. Lead has a melting point of really low, like on the order of 500 Fahrenheit. You can melt that on a metal spoon, and like with a campfire. And so people can make their own bullets that way. So you could make your own lead bullets if you found galena. Just throw the galena into a campfire. You could make lead metal and then melt the lead, and they usually had little metal containers you could pour the lead into to make the musket balls for the bullets. So, but anyways, metals, that's how we get most of our metals, is by doing this way. And here we have titanium dioxide. That is also known as rutile, is the name of it. Pure rutile is a white powder. So, and we use it for a couple of things. We use it as a pigment and a sunscreen. So some titanium dioxide is used as sunscreen. It's also used as a white pigment. The white lines in roads, that's made from titanium dioxide. Now, maybe you've noticed that I guess I'm probably the oldest person in this classroom. The yellow lines, they don't last as long. The white lines last forever, and the yellow lines don't last as long. They used to last a lot longer, the yellow lines, because they would use lead dichromate for the pigment, like a yellowish orange color. And now we use organic compounds, carbon containing, so carbon-based paint. So the yellow lines on the road, they have to be replaced quite a bit. And you can even see sometimes they put like metal on them, and it's like taped on the roads. They don't even necessarily they don't necessarily paint it. But because of that, because we moved away from lead dichromate, you have to replace the yellow lines on the road much more frequently. But the yellow lines seem to last forever because they're titanium dioxide. They're a mineral that lasts a long time. I mean, mind you, I'm not saying like, oh, we should go back to lead dichromate. Of course, lead is a neurotoxin and carcinogen, and dichromate is definitely a carcinogen. So, but I'm just saying it's a practical thing. We have to paint our roads more frequently now because of the concern of the safety of that. Okay, and also look at the amount here. We have 28.6 kilograms of carbon and 88.2 kilograms of the ore. And we're making 42 kilograms of titanium. So if things are made in mass production factories, things are going to be made in like hundreds of thousands of tons. So this is way too small to make in a factory. What this is something referred to as a pilot plant. So this is an intermediate step between formulation and concept ideas to a scale up. And the scale up meaning the factory production. So let me compare it to something a little more close to home, making cookies. Okay, if you've ever made cookies at home, I've made cookies at home. So what do? You take a bowl, and you mixing bowl, and you put your flour, butter, all that stuff in there, mix it up in the mixing bowl, and you turn on your oven, you let it heat up, and then you have your cookie tray, you put the cookies in the cooking tray, you open it up with, put some, well, I guess when you're putting a tray in the oven, you don't need to do it, but when you take it out of the oven, put it in, you can apply it in your hand, take it out, you put oven mitts on, pull it out, take the cookies off, plop more, put it in there. So that's how you make cookies at home. Is that how Keebler makes cookies in their factories? No, of course not. They have a big automated machine. They have these big tanks that mix all the ingredients, and they have something that probably extrudes the cookies. Probably some machine that plops down, it's probably some robot that does this and plops down all the cookie doughs onto a conveyor belt, and that conveyor belt goes over some sort of oven that's heating down, and then the cookies come out, and then they're sorted and put into packaging. So, but let's say, so as you are making the cookies though, so you can use the batch method, like the method you do at home, to get a formula down. To get how much flour I want, how much salt I want in it, how much sugar, that kind of thing. Those ratios can be done using the batch method. So then you get that, and you can get your optimum formula. Now you have to convert the formula into a scale up. And just imagine though, if you're doing a scale up in a big factory where you're pushing through 10,000 cookies an hour, if you heat it up too much, you're going to burn a bunch of cookies, and you're going to lose lots and lots of material that way. You're losing raw materials. Now you have to dispose of the burnt cookies. Now, and you're also losing time because you could make cookies in a time that you're burning the cookies. So you're losing lots of money that way. So how do you make the process work really well? Well, you have a pilot plant where instead of making 10,000 cookies an hour, you're making 20 cookies an hour or something like that, and where you have the conveyor belts, you have a mixing tank, and it's the conveyor belts moving over the heater, that kind of thing. You have these things that are scaled down, so you can get the process down, get the times down, get the ratios, that kind of thing. Like, okay, well, if I run this, I need to have this many packaging materials. Like, why having the wrong ratio of cookies baked versus your packaging thing, that'll cost you time and money too. So you can figure out all these questions at the pilot plants, and then when you scale up, you still have to tweak the process, but you make many fewer mistakes from a scale up from a pilot plant than just saying, all right, we're just going to wing it and make a whole bunch of this stuff. So this is a pilot plant. So we're talking about tens of kilograms, not hundreds of thousands of tons. So, but let's do the math on this. So we're going to look for the theoretical yield, and we've done this before. So we don't know what it is, so let's look at both. So 28.6 kilograms of carbon. So 1,000 grams carbon per kilogram carbon. Mole carbon to 12 grams carbon. And then the ratio of 2 to 1 mole titanium to 2 moles carbon. I'm getting that from the balanced chemical equation. And then, how many grams? Shoot. What's the titanium? 47.9. What? 47.9 what? Oh, we're just anticipating my response. So there's all the units there. And same thing with the titanium dioxide. 88. Okay, so what is 47.9 plus 32? This is, I'm just molecular mass of titanium dioxide, it's 79.9. Okay, and then mole, just mole Ti, sorry. Mole TiO2. So what I'm doing now, I'm converting back to mole titanium, just like I did up top. 47.9 grams titanium per mole titanium. Kilogram titanium to 1,000 grams titanium. Okay, so now we put this in our handy dandy calculators. Okay. 28.6 and this is 57.1 kilograms titanium. And then the bottom one, 2, 52.9. Okay. So So that means that the limiting reagent is titanium dioxide, and the theoretical yield is 52.9. Now, let's say I were the plant manager and I was looking in on this. I would think that whoever's running this reaction is doing a great job. So I would come over, give that person a big pat on the back. Why is that? Well, we have the titanium dioxide and we have the carbon. So what do you think is cheaper, the ore or the carbon? Carbon's cheaper. Carbon's much cheaper. The ore is expensive. So there's an excess of the cheaper stuff to make sure that I can get all the product that I can over the more expensive raw material. But it's not a huge excess. So we're talking about a difference of, on here, it's about 4 kilograms. So, I mean, 8%, less than 10% difference. But that's enough, though, that I know I'm getting all the product that I can out of this titanium. So that was a good move by the person running this. And there's another thing you might see. I didn't do it this way, but I thought about doing this. You can use a unit called the kilogram mole. So what we've been using in class is something called the gram mole, or it's usually just the mole. So a gram mole, so 12 grams of carbon is a gram mole, or typically we call a mole of carbon. A kilogram mole of carbon is 12 kilograms of carbon. There's also something called a pound mole. 12 pounds of carbon is a pound mole of carbon. And pound moles are used in industry, typically only in the United States of America. But kilogram moles can be used other places, can be used in and out of the United States of America. And typically in science courses we use gram moles, or we just call them moles. So moles and gram moles are the same thing. But if you see kilogram mole, pound mole, gram mole in the future, you know what they're talking about. Okay, well, let's go back to the problem. So percent yield is going to be our actual yield, 42.8 all over 52.9 times 100%, as denoted by that formula. And so 42.8 divided by 52.9. So this is equal to 80.9%. And okay, so why is it 80.9%? Why isn't it 100%? Well, when you dig stuff up from the ground, it's typically not pure. Can you find pure things in the ground? Yes, yes you can. Diamonds, you can find perfect diamonds in the ground. They're very rare, they're very expensive. You can find pure gold out of the ground. So, but typically when you get stuff out of the ground, it is usually, almost always some sort of impurity into it. And actually 80% pure, that's pretty pure as far as ores go. So, if you dig up, rutile, titanium dioxide from the ground, it's not going to be a white powder. It's going to be like brown or gray or something like that. It'll be an ugly looking color. It's not going to be nice, clean white color you see like on the roads. It's going to be a really dirty looking rock. It's probably got twigs and stuff in it, and it has other minerals, typically silicates stuck in it. So it's not pure, but we can use it, and when reacting with carbon, we can get nice shiny titanium out of it. So, anyways, back to this problem. So we did limiting reagent theoretical yield. We've done limiting reagents before. The difference here with this one is we had to look at the percent yield. So we were given a yield, and once we calculated the theoretical yield, we were able to get the percent yield from this. but in the end, it's similar to what we've done before. So how are we doing? Anybody have any questions with this? All good? All right. Next problem. 50 grams of oxygen and 850 grams of hydrogen react to make 50 grams of water. What is the percent yield? And so first of all, which one is the limiting reagent? Do you remember from the last problem? We had 100 grams of both. And what was limiting reagent? Oxygen. And 100 grams gave us 112.5 grams. So what is the theoretical yield? Yes, 850. $56.25, that's our theoretical yield. Or you can calculate it out if you want. But I made up those problems, so that's why the numbers are the way that they are. So if you look at this previous problem, we had 100 grams, and we got 112.5, right? And oxygen was limiting reagent. So if we have, instead of 100 grams, we had 50 grams, how much product are we going to have? 112 divided by 2, which is 56.5.25. Right, 112.5 divided by 2. I'm just trying to make your life easier. Some people think A, we're getting 100%. We think B, 90. We think C, 80. D, 70. Is anybody stuck, or you just need more time? More time? Okay. So hopefully you're getting the 88.8%. Well, the Z bar, you know about that? The line over the 8 that's known as a Z bar means repeated. So where do mathematicians go when they go out? They go to Z bars. Who says STEM jokes can't be funny? All right, how are we doing? Anybody have any questions with this? This is the actual yield, 50 grams over the theoretical yield, 56.25 times 100. That's 89%, closest to 90%. Questions? From your nonverbal feedback, it led me to believe that you understood it. Although your energy is pretty low. Rough day, huh? So I know we're jumping around topics, and you guys are having a rough time. I'm having a rough time too. What if I said, you know what, I'm just gonna drink a pint of beer right now, and I took a glass, filled it full of beer, and just slammed it right back? Who would be impressed? One person. What if instead of a really rough day, I said, how about a pint glass of vodka instead? And then I slammed that back. Oh, we got we got an applause here. Wow. Why is a vodka so much more impressive? It's concentrated. Yes, it's concentrated. Concentration. Yeah. I'm not tequila. I can't make everybody happy, okay? Depends on the kind of tequila, though. I've had some bad tequilas. So concentration. Concentration is amount per volume. Like if you can go to the grocery store and you can buy orange juice concentrate, right? You have that tube of orange juice, all the orange juice tasty goodness of a pitcher of orange juice, right? So you take that tube of concentrate and you throw it into water and you get your orange juice. So that's concentrate. There's more stuff per volume. That small tube has more stuff in it. So concentration is amounts per volume. It's amounts per volume. And the unit that we use in chemistry class is molarity, or moles per liter. But there are other types of concentration. So we'll talk about molarity quite a bit. But there is, for instance, there's amount per mass. That's a concentration unit. So like your body fat percentage, like if you're 20% body fat, that's decent. Like if you're 30% body fat, you're like, oh, well, maybe you should think about going on a diet. 20%, you're probably okay. Then you're getting like 10%, like, oh, you're pretty skinny, kind of thing. So that's one way of telling your concentration is amount per, it's mass percent. There's also volume percent, and like alcoholic beverages, we give it in terms of proof. So 80 proof vodka is 2 times the volume percent. So vodka is 40%, depends on the vodka. Vodka is about 40% alcohol to water ratio. So 40% alcohol, 60% water by volume, meaning if I had a beaker, one beaker had 40 milliliters of alcohol, another beaker had 60 milliliters of water, and I pour them together, that's about what vodka is, more or less. And also, the molarity, this is kind of it's like sort of non-obvious when you have molarities. So, I used to work at a company called Ecolab. You ever heard of Ecolab before? They make industrial soaps, and I was working at a manufacturing plant. I hated that job. I mean, some people like working in manufacturing. I didn't like the manufacturing job, but what they really guarded what was called the mixer sheets. So the mixers, they're the ones that made things in huge amounts, and there was a sheet of instructions. So and like the sheet said, like, all right, fill vessel with 10,000 gallons of water. Then throw in 4 of those 50-pound packets of sodium hydroxide lye. Then put 3 pounds of blue dye number 3 and yellow number 7 and that kind of stuff. And agitate for 30 minutes and then add this stuff. And it was just there's this to-do list recipe sheet. Those were really highly guarded because, I mean, well, if you talk about those, you have a formula. Like the formula for Coca-Cola is such a guarded secret. Not really. I mean, if you gave me Coca-Cola and some apparatus to work with in the lab, I could tell you what the formula for Coke is. It'd be pretty easy. I mean, anyone with a little bit of scientific instruments could do that. I mean, think of CSI, kind of thing. People say that also about Techron with it's Texaco now. It used to be Chevron, but Texaco. I'm like, Tecron shouldn't be that hard to figure out what's in it. But formulas are one thing, but then, I mean, they even label it on the bottle too. Anyways, you guys are tripping me out. All right, so but the mixing sheets, those had the process in it. So it was the formula. You could get that from the mixing sheet. Not only that, how to make the stuff. That's lots and lots of investment in there. So, and of course, nowhere in the mixing sheets were a mention of molarity, because the mixers, the people that mixed it up, they weren't chemists. They were skilled labor. They made decent money. They didn't last very long. Because if you were a mixer for too long, you got lots of chemical exposure. So those are the people that get cancers, are the mixers. Also the people in the fill stations, because you would make the stuff and then people would fill them in the bottles. Those people got huge amounts of chemical exposure, and like I said, they get the occupational illnesses. But behind it all, though, we had the mixers, and then they would send samples of things to the quality control lab, and then lots of titrations would happen. And even there, in the quality control lab, there were different, like they had sheets of things that told them what to do. Like, oh, if we get this pH, send word to the mixer, like, okay, add 50 gallons of hydrochloric acid, or do something like that. There were instructions within instructions for things. They knew what to do to tweak the formulas to make sure there was a consistent product. But also, even the lab techs that were there, none of them had, I guess one of them had a chemistry degree, the rest of them did not. But in chemistry, we deal with molarities, and so like the eco lab with all the people with high school education or less working in the factory, they were given instructions, but then behind it all are these molarity calculations. So this is important, but it's not very obvious. I mean, in chem lab, it's obvious because you're given a beaker that says 1 molar HCl. And what is 1 molar HCl? Well, it's 36.45 grams of HCl, which happens to be a mole of hydrochloric acid, and that's bubbled through 1 liter of water. So that gives you a 1 molar concentration. But what I just mentioned, the 36.45 grams of hydrochloric acid bubbled through a liter of water, that's more like a recipe. That makes more sense. So, and that's how we actually make things. So now keep in mind, we're going to be talking a lot about these concentration units, and it's easy to get lost in the concept of them, because it's not, I mean, it's real, but it's not kind of like everyday life. You don't really go home, you're like, oh, I'm going to, I don't know what the molarity is of vinegar. I know vinegar is about 5% by mass acetic acid, but whatever it is, I'm going to go put some 0.25 molar acetic acid on my salad. No, I'm going to put some balsamic vinegar on there, kind of thing. Anyways, so let's go back to chemistry land. So if you dissolve 25.5 grams of potassium bromide to make 1.75 liters of solution, what is the molarity of the solution? Okay, there's 2 ways to do it. I can do the picture and step method. So I can say I have 1.75 liters and I throw in 25.5 grams KBr. Throwing that in there, then I can figure out all the moles of KBr from the mass, and then moles divided by 1.75 liters. I can get the molarity of the solution. That's one way to do it. The other way, which my students seem to like better, is by doing the dimensional analysis. So 25.5 grams potassium bromide. So mole KBr. Okay, potassium is 39.9 and bromine is 79.9. Okay, 39.1 plus 79.9, and that's 119. 119, oh, that's a G. 119 grams KBr. Where am I getting those numbers from? Good old periodic table. potassium here. If you can't see it, you probably can't see it back. It's 39.098. I'm calling it 39.1. And bromine is right here, 79.904. So those added together are 119. And the last step here, just put 1.75 liters. And these units cancel. And so 25.5 divided by 119 divided by 1.75. And this is 0.122 moles kBr per liter, which equals 0.122 molar, capital M, kBr. So, does this make sense? So that's using dimensional analysis. You can do it the step-by-step method if you want. I kind of picture it in my head. If when I read this problem, this is what I picture. I picture it's kind of written as is, but if I'm going to calculate it out, I usually use the dimensional analysis method because I make fewer mistakes this way. So, all right. I know I have this as a chem quiz, but I'm just going to go ahead and do this one. So 50 milliliters of a half molar solution will make what concentration at 200 milliliters? So you can use this dilution equation. M1V1 equals M2V2. That's molarity of 1, volume of 1 equals molarity of 2, volume of 2. Sometimes you might see it as this. And concentration. Concentration is probably better because you could use mass percents as well, or you could use any concentration unit for this. So for this one here, you could, as long as you're consistent with your units, it's fine. 50 times 0.5 equals our 200 of our unknown. So that means 50 times 0.5 divided by 200 equals our unknown. And this is going to be 0.125. So like this. And some of the ways you can do this in your head, so going from 50 milliliters to 200 milliliters, you're diluting it by a factor of 4. So you're going to divide the molarity by a factor of 4. So you're at half molar. Half divided by 4 is 1/8. 1/8 is 0.125. So that's another way you could do it. Does this make sense? Questions of this? Okay. All right, so the next thing I'm going to talk about is solvent and solute. So we're talking about solutions. Solutions are coming up next. A solution is a homogeneous mixture. So most frequently, when you talk about solutions, you mean aqueous water solutions. So aqueous means a solution made from water. There's other solutions. Air is a solution. It's a homogeneous mixture. It's made of mostly nitrogen and oxygen. So it's 78% nitrogen, 20.5% oxygen, 0.9% argon, and water vapor maybe 1%, depending on where you're at. So air is a solution. There's also solid solutions, 14 karat gold, 10 karat gold, 18 karat gold. Those are green gold, rose gold. Those are all solutions. They're made from metals, copper, silver, gold solutions, all solids. But most solutions that we come in contact with are aqueous solutions. And then there's a solvent. The solvent is what is doing the dissolving. It's the stuff you have the most of. And the solute is the least amount of thing, is what's being dissolved. So ocean water is about 96.5% water and 3.5% salts, mostly sodium chloride. So ocean water, the solvent is water, and the solute is salt. What is least? So salt dissolved in water is what ocean water is. Okay, so And I gotta watch. I get stuff from my teaching evaluations. Uh, I do not necessarily promote drinking. I promote legal substances and chemistry knowledge. So, but I'm using this to illustrate using legal substances, solvents, and solutes. So, assuming I know there's other stuff in alcohol, but say just say for simplicity's sake, it's just alcohol and water. So beer is like beer. Beer's got other stuff in it, but let's just say that it depends on the beer, but say a certain beer is 6% alcohol and then 94% water. What is the solvent? Water. It's the most of. How about wine? Wine depends on the wine, but 13% alcohol, 87% water. What is the solvent? Water. How about vodka? At 40% alcohol and 60% water. What is the solvent? Water. Still water. So I've known people that go out and about and they say like this at this establishment, this bartender's awesome. He gave me this drink. It's like pure alcohol. It's all vodka. Nope. Still mostly drinking water. Not going to hydrate you, but it's still mostly water. Also, you go to Prague. There's different types of absinthe, but they can get really concentrated. You can go as high as 70% alcohol and 30% water. So what's the solvent for absinthe? Alcohol, yes. Alcohol is now the solvent. And then 151 rum, that's 151 proof. That's 75.5% alcohol, 24.5% water. And grain alcohol, if you get pure grain alcohol, that is 95% alcohol and 5% water. So grain alcohol is also something known as an azeotrope. So that means that the fraction of the vapor is the same as what's in the solution. So typically, one of the easiest ways to separate liquids is a process called distillation. And you can separate two dissimilar liquids this way until they get to an azeotrope, if one exists. So alcohol is the lighter compound in a water alcohol mixture. And alcohol boils at 87 degrees Celsius at 1 atmosphere pressure. Water boils at 100 degrees Celsius at 1 atmosphere pressure. So alcohol is more, ethyl alcohol, when I say alcohol, means it's more volatile. It will come off first. And maybe you've heard of triple distilled things. It means it's been distilled 3 times. So you make beer. So for vodka, it depends on, you can make vodka out of anything. So Polish use potatoes, those are apparently the higher quality ones. You can use corn, you can use wheat, you can use sugarcane. But you make beer from that, and then you distill it, and you collect the vapors, you condense that down, distill it again, collect the vapors, condense it down, and then do it a 3rd time. So the third stage, the third distillation stage on an alcohol-water mixture is typically 120 proof, so 60% alcohol. And then the triple distilled, then they take that and then they dilute it with water to whatever it is. If you keep on going many, many times, you will get to grain alcohol, and that's 95% alcohol, 5% water. The problem with grain alcohol is if you try and distill it, the vapors are 95% alcohol and 5% water, so you cannot distill past that. You can get pure alcohol, but how do you do that? You take grain alcohol, so the stuff we put in our cars, you take grain alcohol, we usually get it from corn, and you put it through a molecular sieve. It's like this really tiny, kind of like if you have a plastic lid and punch holes into it, you have a really tiny, really tiny holes, and you put pressure on it, and the water squirts out because it's smaller than the alcohol. And you can push out the water that way. That's one way you can do it. Another way you can do it is you can add something that will absorb the water. So when we did the Epsom salts lab, if you're in the chem lab, we dehydrated the Epsom salts. If you throw those back into an alcohol-water mixture, they'll grab the water out of solution. Another way you can do it is you can add something else, typically either methanol or benzene, both of which are toxic. You can add that to the mixture. You can distill that. It'll get rid of leave all the water behind, and then you can then distill it again to get rid of the methanol and or benzene. So those are other ways to purify alcohol. But typically for alcoholic beverages, we typically don't distill it past the third stage, the 120 proof stage. And there's names for that. 120 proof, that's also referred to as white dog. Colloquially, it's called white dog. It can be called Mountain Dew, sometimes moonshine. But moonshine can also be pure alcohol. So, and part of it comes from the old laws. So we have the word proof. The word proof came from, so this is whiskey. You said prove it. The way you could prove it was whiskey was you would take the whiskey and mix it with gunpowder, and if that lit on fire, it was considered whiskey. And then, as such, it would be taxed. So if you could dilute your whiskey down so that it wouldn't catch on fire, you didn't have to pay the whiskey tax. Or sometimes workers would dilute their whiskey down so then, like, oh, this isn't whiskey, I'll just have to take it home and drink it now, kind of thing. So, but the 120 proof, they call that white dog, the third stage. It's called white dog because it's clear and it packs a punch. That's at least what they said at the Bourbon Trail in Kentucky. Also, it was called Mountain Dew and moonshine because of prohibition. So, it was done in the mountains, away from everybody. So that's the Mountain Dew, not just the yellow drink. It makes you hyper. So that's the original term. Mountain Dew came from whiskey, or specifically that. And then moonshine because it was done at night under the light of the moon. Also, so some terms. Bourbon for whiskey. Bourbon has to be made from fresh barrels that have never been used before. Maybe you've seen this in cartoons or things. They have jars that have like X's on them. The X's are the number of times the barrels have been used. If it's never been used before, it has no X's on it, and then that product can be called bourbon. So bourbon has to be at least 50% or more corn and can only have wheat, rye, or barley as the other grains. But most bourbon is either straight corn whiskey or just very heavily. If you add other things, it changes the flavor a little bit. So Irish whiskey and Scotch and other whiskeys, they don't require the one barrel only. That's only for bourbon. And most bourbon's made in the United States. The other thing is you put the 120 proof, so put the third stage, the white dog, into the barrels. Hawaii wouldn't be a very good place to have a distillery to make bourbon. I guess you could. There's a little bit of seasonal change. They usually make it in Kentucky and Tennessee because when the seasonal changes, the temperatures causes the wood to swell and retract, and then the alcohol can be drawn into the wood and then pushed back out, and the flavors can go into the whiskey. And some of the alcohol evaporates, and the alcohol that's lost through evaporation, that's called the angel's share. That was told. So Irish and Scotch whiskey makers, they're very Catholic, and that was their like, oh, what's happened? Oh, it's the angel's share kind of thing. So the angels get a cut too. So whiskey, of course, is not at it can be 120 proof, but it's when stuff you buy in the store, it's not clear, it's brown colored. The brown color comes from the wood, and and the cask strength is usually on the order of 90-ish proof, so you do lose 30% or more alcohol by the angel's share of sorts. So, but that's just okay. So that's just personal interest. Again, I'm promoting chemistry, not alcoholism. Okay, and types of aqueous solutions. I already said solutions are homogeneous mixtures. If you've had me in lab, you've already seen this. If you're having lab this week, you'll see this. There's different types of electrolytes. So there are strong electrolytes. So, let me back up. Pure water does not conduct electricity all that well. So my grandmother, when she was a teenager, she was swimming in a freshwater lake, and it got struck by lightning. And she said she felt a little bit of a buzz, a tingle, but it wasn't that bad. It didn't defibrillate her. So lightning bolts are very powerful. We're talking like 1,000 amps and 100,000 volts. So Lightning bolts have a ton of energy, a lot more than a ton. They have lots and lots of power in a lightning bolt. So if it was able to just give a mild shock to my teenage grandmother and did not defibrillate her, I'm here today, right? So water does not conduct electricity all that well. But if one were to add a strong electrolyte to water, water would conduct electricity. So salt water is a good conductor of electricity. Like in the ocean would conduct electricity well. But the ocean's getting struck by lightning all the time. So but it's just the ocean's just so huge, it doesn't really matter. But if you're right next to a lightning bolt when it strikes, then there could be some problem, especially if you were grounded somewhere. Then the current could flow through you. But so strong electrolytes, and they have to ionize. They have to break apart. Weak electrolytes, these are molecules that like to stay together, but they break apart a little bit. So vinegar, so acetic acid is an example of a weak electrolyte. It likes to stay together, but it will occasionally break apart. So that's kind of like the analogy I like to use is like my wife and I on our honeymoon. We were like weak acids. We spent a lot of time together, like sat next to each other in the plane. We went around, but we didn't go to the bathroom together. That was cool. You do your thing. I'll wait my turn, or I'll go to the men's room. You go to the ladies' room. That's cool. Kind of thing. So we were together quite a bit, but not all the time. But then when we got back together, we went back to holding hands and whatnot, right? So that's what a weak acid's like. So acetic acid has this hydrogen attached to it, and then it can break apart sometimes, but it feels a loss, and then it gets back together as soon as it can. That's a weak acid. So slightly ionized. And then there's a non-electrolyte. So sugar is like this. Sugar water is not a conductor. Ethylene glycol water solution, so antifreeze in water, does not conduct. Those are non-electrolytes. They do not conduct at all. So you'll learn about that. Has anyone ever seen the movie Idiocracy? Yeah. So electrolytes, that's what plants crave, Just like Brondo. Okay, and we're going to end soon, but let me talk a little bit about the solubility rules. What makes things soluble in water. Something to note, and when things dissolve in water, generally speaking, the attraction between the ions and the water is stronger than the attraction of the ions themselves. So frequently, it's usually 6, can be 4, depends on what's in there, but like a sodium ion will tend to get, and you haven't learned about polarity and whatnot yet. So water is a polar molecule and has a negative end and a positive end. So a sodium ion will have 6 waters surround it, and likewise a chloride anion will have the water's pointing it has 6 as well, but the water's pointing in the other way so that the hydrogens are attached to it. These 12, so 6 on each, these 12 waters attached to the 2 ions have a greater attraction, Coulombic attraction, than the 2 positive and negative ions. So then because of that, it will dissolve. But something to note, the things that are water soluble are the ones with a small charge and the big, we haven't talked about sizes yet, but alkali metals, they're big atoms. So they're really big atoms. So you have a very big ion, relatively sized, with a very low charge. If you have a small ion that has a big charge, that's not water soluble. So things like phosphates, so PO4 -3, so a -3 charge, that is not soluble. It does not, because of that big, huge charge is going to keep it together. So the general trends we'll talk about next class. The alkalis tend to be soluble, nitrates, acetates, halides, those kind of things, and contrast it to the other things that tend to be insoluble. So I want to have the classes aligned, so this is where we left off in the other class, so I'm going to end class 5 minutes early. Unless anyone has any objections, we can talk about idiocracy more. But, okay, anybody have any questions? If not, okay, free to go. I will stop the recording. And don't let the Vice Chancellor for Academic Affairs know that I've let you